welcome to the Recitation 0C, Introduction to PyTorch. Today, we'll explore the various functionalities of this framework for training a neural network. Prior knowledge of Python and object-oriented programming is the only prerequisite for this recitation. If you need a refresher, please watch Paul's recitation on Python and OOP before this one. Python is one of the popular deep learning frameworks. While each framework comes with its own learning curve, mastering one makes it easier to learn others, as most of them use the same underlying concepts and ideas. The popularity of PyTorch is due to the great flexibility it provides for research and prototyping as compared to other frameworks such as TensorFlow, JAX, Caffe, etc. On the flip side, TensorFlow is known for being production grade. If you're using Google Colab, PyTorch comes pre-installed. For your machine, you can install the latest version of PyTorch using either pip or conda. Based on your graphic card, you might have to install an older version. Check this link for the corresponding pip or conda commands. If your device lacks a graphic card, you can also install the CPU version. However, using Google Colab or a cloud VM with GPU is recommended in this case. Uni's recitation covers Google Colab, Rooming and Arjun explore Amazon Web Services, and Vish introduces Google Cloud in his recitation. Now here's a list of libraries we need pre-installed. While this recitation does not require prior knowledge of NumPy, an understanding of NumPy n-dimensional arrays and the operations that can be performed on them transfer well to PyTorch tensors. If you're new to NumPy, make sure to check Prakriti's recitation on fundamentals of NumPy. Matplotlib is for visualizing the dataset and predictions of a network, while Torch Summary X is for exploring model architecture. If you're using Google Colab and this code snippet shows device as CPU, go to Runtime and select Change Runtime Type, then ensure GPU is selected for hardware accelerator, and then click Save. This entire notebook can be executed on the free version of Google Colab. Let's say our objective is to model the Boolean operator exclusive OR using a multi-layer perceptron. Now this is an interesting problem because a single neuron cannot learn this function. However, 3 neurons put together in this fashion can exactly model this function. Here, the first layer of 2 neurons is called the hidden layer, and you will learn more about this in lecture 1. This recitation will give a bird's eye view of many concepts that will be explored in detail over the semester. Now, to begin our deep learning project, we need a labeled dataset. As this is a simple example, we can generate a synthetic dataset very quickly. PyTorch provides us with 2 classes in this regard, Dataset and DataLoader. Dataset is an abstract class that we implement for our custom data. Now, unless we are using the built-in datasets provided by PyTorch, we almost always end up writing a custom dataset for every deep learning project. On the other hand, we usually do not have to write a custom data loader. In most cases, we can instantiate an object of the default data loader class with our custom dataset as input. The role of data loader is to make the dataset iterable so that our model can easily access the samples and their corresponding labels. In the XOR dataset class, the function's length and get item comes from the abstract dataset class. As the name suggests, they return the total size of the dataset and individual samples by index respectively. Here we generate the inputs for XOR in continuous space. Before going further, let us double-click on the tensor operations used here. PyTorch tensors are quite similar to NumPy n-dimensional arrays, with 2 major differences. 1, they can leverage GPUs, TPUs, and other hardware accelerators for performing a large number of calculations in parallel. And 2, they're optimized for something known as automatic differentiation. We will come back to the second point multiple times during this recitation without going into too much detail. We have a future recitation specifically dedicated to computing derivatives and automatic differentiation using PyTorch AutoGrad. RandInt creates a tensor of the desired size, where each entry is a uniformly generated integer between low and high. Here, low value is included and high is excluded. Hence, all values in the data tensor are either 0 or 1. The d-type parameter converts these integer values into float. RandN, on the other hand, creates a tensor of the same dimensions as data tensor, with each value being generated from a normal distribution, with mean 0 and standard deviation of 1. Here are a few more ways of creating tensors with commonly used values. Ones and zeros create a tensor with all values as 1 and 0 respectively. I creates an identity matrix. Rand populates its values from a uniform distribution between 0 and 1, where 0 is included and 1 is excluded. A range works quite like the range function of Python, that it generates a one-dimensional tensor from value 0 to the number parameter -1. The appendix covers more ways of creating tensors and various mathematical operations that can be performed on them. Now let us visualize the dataset we just created. Note that we assign output labels to the generated input points before adding Gaussian noise. So if the standard deviation is too large, we are likely to end up with points that are way too far from the original register and hence appear to be misclassified. Here we also see a conversion between PyTorch tensors and NumPy ND arrays. Data.cpu moves a tensor to CPU memory. As we discussed before, PyTorch tensors can access both CPU and GPU, while NumPy can only work with CPU. Sometimes tensors also have to be detached from the computational graph before being converted to NumPy. Like this. We will cover this in more detail in a short time. Converting from NumPy to tensor is pretty straightforward. Here, the return tensor and input NumPy ND array point to the same memory, and future modifications of one will automatically reflect in the other. Now, with the dataset created, let's create the iterable DataLoader object. Here, batch size denotes the number of samples to be clubbed together into a single batch. The higher the batch size, the greater the memory requirement, and lower the compute time for training once through the entire dataset. Shuffling the dataset is recommended during training, as there is no special significance in the order of samples in the dataset. Number of workers create additional subprocesses for loading the dataset. Again, it reduces compute time at the cost of memory overhead. Pin memory speeds up the transfer of data from CPU to GPU memory. Drop last can be used to force all batches to be of the same size. This can be used in training, but make sure you set shuffle equal to true, or else you will be missing a few values every time from the training dataset. All right, let's move on to the main part of our project, the architecture of our network. We intentionally kept it simple. As discussed before, a single linear classifier cannot learn the XOR function. Hence, we're using two linear layers here. This 2 corresponds to the dimension of the input, as XOR is a binary operator. This 2 and this 2 corresponds to the dimension of the hidden layer. The output features of the previous layer must always be equal to the input features of the next layer. Finally, this one corresponds to the dimension of the final output. Overall, this architecture is quite like the multi-layer perceptron we saw earlier. We also added a tanh activation between the two linear layers. Wait for the lectures to learn what happens if we do not have an activation between linear layers. Sequential ensures that the output of one function in the list is fed as the input to the next function. This simplifies the forward function to a single line. Note that we didn't write any backward function. This is because PyTorch automatically takes care of backward propagation for any custom network architecture using the computation graph for automatic differentiation. Our custom network architecture can also be spread across multiple classes, and PyTorch will still handle backward propagation for us. To understand the model, we can either directly print it as a string or loop through its named parameters. This requires grad equal to true shows that the tensor is attached to the computation graph, and device equal to CUDA 0 shows that the tensor resides on the first GPU. If your machine has multiple GPUs, you might see CUDA 1, 2, or 3, etc. To convert such a tensor to NumPy ND array, we must first detach it and move it to CPU, or else we'll get a runtime error. We can also print a summary of our model by sending in a sample batch of data. Note that both the model and data should be on the same device, GPU in this case, or else we'll get a runtime error. Here, 8 denotes the batch size and 2 the number of input features. With the dataset and model ready, we need to decide on a loss function and optimizer. The choices made here might look arbitrary at this stage. That's fine. Over the semester, you will study many loss functions and optimizers in great detail and will develop an understanding of what to use and where. As the output of an XOR is either 0 or 1, we are working on a binary classification problem. For every data point, our network will predict a label that will either match the correct label as per XOR output or not. We need a loss function to assign a numerical value to all wrong classifications put together. A nice solution could be to simply count all the misclassifications. However, we also want to iteratively train a network to reduce this misclassification as much as possible. Hence, we need the loss function to be differentiable with respect to parameters of the network. This will help us to numerically move toward the desired parameter values that result in minimum loss. The computation graph keeps tracks of these derivatives, while it is the job of the optimizer to update network parameters based on computed gradients. Binary cross entropy is a common loss function for binary classification problems. You can check out this video for a short explanation or wait for the lectures to cover cross entropy in detail. Always check the documentation of the loss function you intend to use, as some also implement an activation function together with loss. This is usually done for greater numerical stability or efficiency. BCE with logit loss implements a sigmoid function, along with the binary cross entropy loss. Hence, we do not use any activation after our last linear layer. For the optimizer, we are using stochastic gradient descent. Now, a word of caution here, especially if you're training a model on GPUs. Make sure to move your model to GPU before you initialize the optimizer with model parameters, or else no learning will happen. We also generate a larger training and validation dataset and the corresponding data loader. We train the model on training data and use validation data for manually tuning the hyperparameters. We usually also have a test dataset that is completely unseen by a model for benchmarking its performance against other models. For this simple problem, we will follow this test dataset and benchmarking. Let's move on to the training loop. To make the code modular, it's a good practice to write a training and validation function for one epoch separately, and then call it a training loop. Here, we set the model to train mode and iterate through each batch in the train data loader. The train mode is needed because certain torch.nn modules, such as batch norm, dropout, etc., have different forward steps for training and evaluation. As the model is on GPU, we also need to move the data to GPU. Our final layer had output feature equal to 1. Hence, we have a single output for each data in the batch. We use squeeze to reduce this two-dimensional array into a one dimension. Next, we calculate loss by comparing the model predictions with true labels. The return loss is a zero-dimensional tensor and can be converted to scalar by calling the item function. Now comes the backward propagation. By default, PyTorch accumulates gradient over subsequent backward passes, and with every call adding on to the existing gradients instead of overwriting them. This is desirable in some specific cases where we want to compute the gradient of the loss summed over multiple batches. For every other case, we must zero out the gradient before performing backpropagation for each batch. Here, based on the gradients, the optimizer updates the model parameters, and finally, we calculate the accuracy of our predictions to return the training loss and accuracy. Just like we use squeeze above to reduce a tensor dimension with only a single element, we can also unsqueeze to increase dimensions. We can unsqueeze along any dimension and unsqueeze as many times as needed. However, we can only squeeze dimensions with a single element. Applying squeezing along dimensions with multiple elements has no effect. You should also go through the appendix for more such tensor manipulations like flatten, permute, etc. Now, the evaluation function. We set the model to eval mode and iterate through each batch in the val data loader. Again, move the data to GPU as the model is in GPU. Note the use of torch.inference mode. This is new here. In some other places, you might see torch.nograd. This is used to locally disable gradients as we don't need them during evaluation or testing. While we calculate validation loss to compare it with training loss, we don't do backpropagation here. Finally, we return the validation loss and accuracy. With the training and evaluation functions done, the actual training loop looks very simple. We arbitrarily decided to run the training for 100 epochs. This is a hyperparameter and you may need to run for more epochs or implement early stopping based upon your problem. Also, we are using a fixed learning rate in this simple problem, while you may need a scheduler to reduce the learning rate as your model improves for your projects. Finally, this model trains very quickly. For more complex problems, you should consider using PQDM for showing progress bars and print intermediate results. With everything done, let's visualize our model's performance. If all went well, the model should reach close to 100% accuracy. If not, train it for more epochs or make the network architecture deeper or wider. In the figure, you can see prominent decision boundaries parallel to the diagonal. Your decision boundaries could also be parallel to the other diagonal as seen in the slide. A challenge question. Can you explain why the decision boundary is sometimes along one diagonal and sometimes the other? Can you force it to go one way or the other? For more complex network architectures, you'll see curves around the clusters instead of straight lines. Why do you think that's the case? Another challenge is to train a neural network to model more complex decision boundaries, like the pentagon you'll be seeing in the first lecture. Again, you'll have to generate synthetic labeled data using a custom dataset class and wrap a data loader around it. I suggest using a uniform distribution and labeling it before adding a small Gaussian noise. Figure out what network architecture works best for you. As it is still a binary classification, you can continue using the same loss function and optimize it. Finally, you may have to save your fully trained model, or sometimes save a checkpoint after every few epochs and load it in case your training gets interrupted. Because life happens. Even though the extension here doesn't matter, the common PyTorch convention is to use .pt or .pth. You can even store the optimizer and scheduler state dictionary along with the model. This is recommended for intermediate checkpoints so that you can resume training exactly as you left before the interruption. An important point to note here for Google Colab users. By default, Colab stores the checkpoint in the hosted runtime. This storage gets deleted if the runtime gets disconnected or if Colab crashes for some reason. To ensure you don't lose hours of your training, you should always save a checkpoint in Google Drive. This code snippet mounts the Google Drive after requesting user authentication. Subsequently, you can use this path to save model checkpoints into Colab Notebooks folder in your Google Drive. The recitation ends here, but I strongly recommend you go through the following appendix to improve your understanding of how PyTorch sensors work. We'll also provide a cheat sheet for PyTorch sensors on the course website for easy reference. Thank you for your time. If you have any questions, please reach out to the course staff on Piazza. We'll meet again in the first recitation after a couple of lectures and explore the training of MLP in much more detail. See you then.